Now the Fourier transform is just an example of an integral transform, and there are many different kinds of integral transform. You may have heard of a Laplace transform, which is something that's often taught in maths, and it's also very useful in physics. But here we're talking about the Fourier transform. So an integral transform in general looks like this. We have some function of real space, and in this example here I've chosen the t for the variable time. Then we have something called the kernel, and the kernel is a function of the real variable, t for time, and some transform variable. In this example I've chosen w as our generic transform variable. Then we integrate, and what we end up with is the transformed function. When we integrate over t, the t goes away, and so the function over here will just be a function of w, and it's now in w space. Every useful integral transform also has an inverse transform that turns the function of transform space back into a function of real space. So you have some function of time, you transform it into a function of w, and you can inverse transform back to a function of time. For the case of the Fourier transform, we have functions in real space, which would be time or actual space, x, and in the transform space we have frequencies, so there will be the temporal frequency like omega or the spatial frequency k, and the inverse transform takes it back to functions of space or time. Now, just to give you some idea of how Fourier transforms are used in physics, there are a couple of different ways. One is to solve problems, for example differential equations. And there might be some problem, you set it up with a pile of differential equations, and you're looking for a solution, and you try and go straight from the problem to the solution, but there are dragons in the way preventing you from getting there because your system of equations is horrible and you can't solve it directly. Sometimes it's easier to take the Fourier transform of your equations and look at the transformed equations, and then you have a simple matter of lying on your back, sipping cups of tea while you write down the easy solution in transformed space. Now sometimes understanding the solution transformed space is enough. Other times you may wish to take the inverse transform to actually get back into the domain in which you started, be it time or space. Another way in which Fourier transforms are often used in physics is to understand strange data, or to filter data. So you might have some data which is maybe an acoustic signal, for example, and you want to understand what's going on, and you try and look at the data as a function of time, but there are dragons of confusion in the way that mean it's just too hard. Often, it's easier to take the transform of the data and look at the transform data, or in this case, if it's a function of time, what we'll see is a frequency spectrum. And you might see some spikes at particular frequencies that you could filter out, for example, and clean up your acoustic signal. So you take your transform data, you can process it, and understand it easily. And as ever, there is the option perhaps of transforming the signal back into the time domain again.